Good morning, mathematicians. Yeah, welcome to a new episode. It seems like I'm starting later and later. Not intentionally. My schedule just shifts sometimes, I guess. Yeah. Also, today I'm really tired because yesterday I went up and down the Calgary Tower 8 times over the course of 2.5 hours. So, Calgary. 802 steps or 30 floors. They open it every Tuesday in March. It's open to the public, and you just go up the stairs and down the stairs. Well, I mean, you stop and appreciate the view at the top, but yeah, you see how many times you can do it. And so this week I did 8. So next week I'm going to try and do 10. I started late, so I'll do the full 3 hours. I'll try and do 10. That's my goal. But what's also neat about that, this is it's not just me bragging about my whatever. Oh, we've got some viewers from Italy this morning. Wonderful, wonderful. I went to Italy 3 summers ago. Actually, I have a video about the summer school I went to for proof assistance and homotopy type theory. And but I decided to stay a bit longer in the morning. Or sorry, my brain is dead. I'm so tired today. I decided I went early before the conference, and then I stayed also a bit late to go to around Italy. And actually, I have a friend who's a Ph.D. student here who joined me in the first half. So he's from Italy, so I stayed with him in a town just outside of Verona. Anyways, loved Italy. It was fantastic. I mean, it's not a very controversial opinion. I think lots of people like it. I did a little bit of math tourism as well. You know, saw Galileo's middle finger in the Museum of Galileo, and there was some old. Oh, there's like in Venice, there was like a really old university of mathematics. We found the old like math department building. Anyways, basic category theory question: what is the best way to understand tensor product of morphisms? I've seen it in a lot of constructions. I think that's context dependent. Let me answer that in 1 second. I just want to say something about Richard Guy here, who I have up on screen. Yeah, so he's a famous mathematician in combinatorics. He used to be at the University of Calgary, but he passed away actually just before I got there. But you know, he collaborated with tons of people, and he was also like very prolific in combinatorics, but I think also known to be a good like expositor, and he really liked like mathematical games and having fun with mathematics like that. So you can read about it here, but oh, I didn't even know about his chess problems. But what's also cool is that so one thing about the Calgary Tower, he used to do the climb every year, and even into his 90s, he was going up like multiple times. Him and his wife both did together, and then I think she passed away first, unfortunately, and then he would very sweetly carry her picture up with him when he did. And there's actually there's a picture of his wife Louise Guy in the tower when you're going down, and some selected poems. I think they're like poems from high school students that won some competition or something. So anyways, check out Richard Guy. Check out his work. Cool stuff. Okay, let's talk about category theory. So, basic category theory question was the best way to understand tensor product of morphisms. Well, I don't know. Tensor product of morphisms. Well, I don't know. Yeah. So like I was starting to say before, there's different context for the tensor product. There's different ways you can define it. Like what is the tensor product of two vector spaces, for example, and that sort of shapes the way that you think about things. For me, and I think for a lot of people, I like using the definition of tensor product. Well, okay, so first off, I have a video series which is incomplete but has answers to a bunch of your questions, I think, on tensor products. Where I talk about the formal definition of a tensor product, like the rigorous definition. So by that I mean, construction, like an explicit construction of this as some quotient space. And I also talk about the universal property that the tensor product satisfies in that video series. And but the point is, so okay, there's the rigorous stuff is all there, and now let me say non-rigorous things. Like what are elements of this vector space? They're formal sums, which is a word that bothers me. I think it should be made more rigorous, but they're basically just sums of some number of elements, maybe with scalars. These aren't bases elements that I'm talking about. They're just sums of elements, possibly with some scalar in front, although you don't really need to write this because you can, absorb it in. Right, so like this is one of the things about tensor products and why they have a relation to bilinear maps, because alpha times this tensor is the same as multiplying this vector, and taking the tensor is the same as the tensor of these two vectors, for example, right? Okay. Now, what is a tensor product of two maps? Well, of two morphisms. Actually, well, let me trudge ahead, and then maybe we can. There's maybe more than one way to answer it. So first off, one thing to notice is that the tensor product is an example of a functor from vector spaces to themselves. So what that means is, so fix some vector space V, right? Fix some vector space V. Now we get a map on vector spaces where I send a vector space to the tensor product of V, for example. So it's a map on objects. Moreover, it's also a map on maps, by which I mean if I have some linear transformation between T and W, then okay, I apply my drew that the wrong way. I apply the tensor product to each of these factors, and I should get a corresponding map between these. So what is that map going to be? It's going to be the identity in the first component and the map T in the second component. So what does that mean? what does that map do? Like, so the identity on the first component tensored with the identity on the second component, that acts on a simple tensor, VW, by, well, as you might imagine, it'll just be the identity on the first component, and in the second component, you spit out TW. And then by simply demanding that this be a linear transformation, it's enough to specify it on the simple tensors, because then we just force it to satisfy additivity. So a lot of constructions have things like fxid, which I think of as mapping a pair while fixing the second element, but that is not rigorous. Yeah, I think it's fine to define things that way, right? Like, well, okay. So I mean, technically there is something you could check, right? Because there is something to check here, because so let's say this map, right? I'm claiming that this symbol I've drawn here is a map on tensors, but how do we know that this is well defined, right? Because, for example, we might have taken as our concrete model for the tensor product, we might have taken this so like the tensor product of V and W. You basically, one explicit way to give the construction is to you look at the Cartesian product, and then you basically quotient out by all of the relations that force bilinearity, and when we write V tensor W, so this is again like this is all in, well, A, it's in Alufi, B, it's in my video series on tensors. But what we mean when we write V tensor W, we mean that's actually just a shorthand for the equivalence class of the pair VW. And so therefore, if you want to, if I'm going to make this claim here that this is a well-defined linear transformation, well, I better show that in fact that this is well defined. So what does it really mean to be well defined? Well, I just basically need to check that it satisfies the bilinear relations, right? So in other words, I need to check that id t of alpha v w is the same as id tensor t of v alpha w, and then same thing with pulling the scalar out in front, and then you should also check the bilinear relations like VW plus U tensor W satisfies additivity. So, well, universal products need not be literally represented as pairs tensor products are, so we can do this. I'm not totally sure what you mean by that, but yes, this does come from bilinearity. So the way that I would write this, and we can actually use the universal property here, right? So the universal property says, well, we're sort of doing, so this would be V cross U, I guess. Did I write things weird? Yeah, so I guess we're looking at V cross U, and we want to define a map into V tensor W. Or rather, we're going to start with a map. I'm gonna call this map. I'm gonna call it I cross T. And this is our this is our map into our tensor product, which is this is the projection map. So by which I mean this is just the map that sends the pair v comma w to the coset of this subspace generated by all the bilinear relations. And so the universal property says that for every, if you can show that this map is bilinear, then there exists a unique map making this diagram commute. So, and I'd maybe call that I cross T, right? So then what we could maybe do is like, so we start off like, so this I cross T, I'm just not writing the D for id because I'm being lazy to define this. What we could really do is just first off start by defining a map I cross T. And then, so you start by defining some map I cross T on pairs U and V, and you define that to be, so here it's landing in the tensor space, so it'd be V cross T, or sorry, this should be VU, sorry, other way around, V tensor TU. What about the case of a non-tensor product of morphisms, as in the construction of the exponential object? That I'm not sure. You mean just a product of morphisms in general? Like the work, but new to commutative diagrams. Is there a video you describe what the different arrows mean? Oh, so like, you mean like, why is this one dotted? So one thing I'll say is, so normally like an arrow is it like, we'll put a name beside it, and that tells you what the arrow is. You know, so like I said, I put this name beside this arrow, pi, that tells you it's a projection map. I put I cross T beside this arrow, that tells you it's that map. But now the dotted arrow, normally we write that in a diagram when that arrow is sort of forced to exist. So like by definition, right? So for for example, here's another example. So, my brain's not working properly, so we'll see if I get this right. But I think it's suppose we have a group homomorphism. I don't know if that's comfortable for you or not. But one of the properties of quotients is that if you have a normal subgroup, then if the kernel of phi is contained in N, so here this map is the on the left, the pi is just the projection map sending an element to its coset. Then there exists a unique map making this diagram commute. So we might call it N tilde. So in this case, you know, I don't have to write this as a dotted line, but it's just a normal convention. Let's say you make this line dotted if this is the line that is sort of forced to exist by the universal property. So you can sort of look at this diagram, and even without the symbols, you can sort of guess that because this line here is dotted, you can guess that, okay, the input data is this line, and then I'm writing the dotted line because there's some way that line can be constructed from the other two. So that's a common thing. So I don't know if that was your main part about the questions of commutative diagrams. I can talk more about the other arrows as well, but I don't have a video on that at the moment. Question: managed to prove that finite dimensional reps of a Lie algebra slash algebraic group are Weil invariant. But my proof doesn't use a finite dimensional assumption. I know that there are some infinite dimensional counterexamples. Proof too long for chat. The weights of a representation are Weil invariant. Let me think about that for a second. The weights are Weil invariant? Yeah, that should be, yeah. But you think there's counterexamples in infinite dimensions? I don't know why that would be the case. I'd have to crack open my book on category O. Looks like I'm defining two different types of products on morphisms, tensor products, and universal products. Oh, okay. Right. So, So, I wouldn't use those names. I wouldn't call one a universal product of morphism. So rather, this thing I wrote down here, I cross T. Yeah, I don't know what I'd call it. Just a product of morphisms, maybe. Yeah, but then the thing that it induces. So if this is bilinear, so yeah, I guess what I'm writing down is a bilinear map, and if I and then the map that this induces, I would call the tensor product. So you can get this from the universal property. But you also don't need to even use the universal property here. I think this is just a nice way to do it. You can just go back up to here, define your tensor product like we did, and then just check that it's well defined on equivalence classes. It basically amounts to the same thing. Yeah. Yeah, Verma modules would be counterexamples, or some stuff in the discrete series of SL2 SL2. Oh yeah, I guess I was thinking about Verma modules. I didn't think Verma modules would be a. I'm not. I've studied like the category O stuff a little bit, but I am not an expert, so don't trust anything I say on this topic. I didn't think that Verma modules would be a counterexample, though, because those sort of have this nice. They're also built out of this nice theory of like weights and root systems and stuff, and the Weil group plays nice with your root systems. So I didn't think that would be an issue. But I don't know. Maybe. Shoot me an email or something if you got more time. I'd be curious to improve my own understanding. Maybe give me an excuse to crack that book open again. I see there's this question. So someone asked about what the dual lattice represents geometrically. That's a good question. The dual lattice. Wow, chat's asking me a bunch of stuff I don't know today. Yeah, I don't know if I have a good answer. I don't know if I have a good answer off the top of my head. Well, you say dual lattice, and then you also read a quotient. Yeah. I'm not exactly sure the best way to think about that. V tensor U strictly the range or just the codomain of pi? Yeah, V tensor U will be the range, right? Because V, like V tensor U, again, this is, well, there's different ways to define it, but I normally think of so there's the universal property, but I don't really love the universal property because it doesn't I do love the universal property. I use it all the time, but it's not, in my opinion, a complete. It's a complete definition, but you still need to show that something exists that satisfies the universal property, right? And so, in order to give a concrete construction of this, so I think my email. I'll drop my email in chat here. Actually, I think I'm gonna. I'll send this email to you now. Actually, maybe I'll send you my academic email. I think I'm gonna set up, like, this channel is associated to my ordinary Gmail, but I think I'm going to set up a new, like, channel specific email. Yeah, so that'll be somewhere. My Gmail is available somewhere on this YouTube as well, but I might take it off soon and get a channel specific one. So, so we have V tensor U, and like this is supposed to be like one way to define it is this Cartesian product of V and U, and we mod out the bilinear relations. So as vector spaces. Rather, I might have even misspoke. We might even just straight up take the free vector space. Actually, sorry, yeah, I lied. I think we take the free vector space on V cross U, which is absolutely massive, and then cut out by the subspace. So the point is, I mean, okay, if you don't know what that is, like, don't worry about it. Also, go watch my video series on tensors. But the point is elements of this space are just cosets. There's some pair plus this subspace of relations, and so the projection map from V cross U into V tensor U is surjective. I mean, first off, I mean, this thing has, like, insane infinite dimension. But also you can just see it because, well, everything in the tensor product is just cosets of this form, but that's exactly equal to the image of pi applied to VU. For a bilinear map, we can answer that component-wise. Oh, sorry, I didn't look at chat around the time that message got sent, so I'm not exactly sure what part that applied to, but yeah, but bilinear maps are yeah. Thoughts on Topos theory by Goldblatt? I've never read it. I also don't know a ton of Topos theory. I've known enough to get by, which I haven't needed a lot. And also, I mean, I have a copy of Sheaves in Geometry and Logic, and I go and I flip that book open from time to time and try and get a little bit further. And it's, again, one of those things where I would love to learn more Topos theory and to really get into the weeds. Like, I want to understand the logic of Topos theory, and in that book they sort of rework the forcing arguments and stuff like that. I'd love to learn that all one day, but yeah, there's only so many hours in the day, and I need to publish papers. So publish papers in a field that doesn't really have a lot to do with topos theory and logic. I mean, it does have to do with topos theory and algebraic geometry. Like there's stuff with like the étale topology and like the FPPF site, FPQC or whatever it is. Like I haven't really learned any of those properly, but just sort of like again, enough to like just get by, because like, okay, we need those things like in what I'm doing. But no idea what a topos with a 3-valued omega means. I have another totally unrelated question, if that's okay. Yeah, that's why I'm here. That's why I'm doing these streams, so you can listen to me yap about chaotically different things. I understand that monads are monoids internal to an endofunctor category. Are there groups internal to such a category, other structures? Well, sure, you can have a group internal to any category. Yeah, like a monad, like, okay, a monoid internal to an endofunctor category. That also doesn't have to exist, right? Like a monoid is just a particular kind of. I mean, okay, examples do exist, right? But like, if you just pick an arbitrary endofunctor category, look at the category of endofunctors on it. There's no a priori. I mean, well, maybe probably there's some way to like trivially construct a monoid. In the same way that like, oh, you can define like a group on any set or something like this, right? You can always find some way. There's always like stupid degenerate examples, but yeah, so like a monoid doesn't know it, like it depends on your category, like in the same way like your category doesn't, like an arbitrary category doesn't have to have products, or by which I mean, products aren't always guaranteed to exist, but they still might exist for some objects and not for others, something like that. So in the same way, you could have a category that has group objects, or a category that doesn't have group objects. Like, I think on the stream a couple days ago I talked about the axioms for a group object in a category. How can we think of groups internal to the endofunctors from Haskell programming? I don't know anything about Haskell, to be honest. Replace a group with something else other than a monoid. I was thinking maybe the functor that sends f to its opposite category, which is isomorphic to. Yeah, could be. Yeah, I don't know. Unfortunately, I don't have an answer to your question, but I'm sure there's a bunch of programming like monads and monoids are abundant in programming. And in describing programming concepts in terms of category theory, this I know. And so I wouldn't be surprised if you could write down interesting examples of a group object internal to a category that had significance in programming. But I don't know of anything off the top of my head. That's just the tensor product. Most of the tensor algebra I've done was with repeated index notation. Of course, this is the general case. So you can, you can then have so I just talked about taking a tensor product of like two spaces, right? But of course, you don't have to stop there, right? You can take a tensor product of however many spaces you want, and you can have a tensor product coming from some other number of spaces, and then now, yeah, you're gonna have like in the same way that like if you imagine let's say a map from Rm to Rn, nothing to do with tensor products. I'm just talking about like coordinates and stuff, right? So one way you could write this map is so like x1 up to xm. So we'd call it f of this. Well, there could be one component map. So I need to give you an element of Rn. I need to specify n things, and so for each of those n entries, there could be a separate map f sub I. So f1 for the first entry, and each of these maps depend on each of those m variables, right? So that's the basic idea behind like this multi index notation. Yeah, that's the basic idea. So in the same way, like your linear transformation, like maybe you have these other, for like a linear transformation between two spaces of tensor products, you might need like, yeah, all of these other like indices to sort of keep track of where it's sending which variable there, and you can just sort of think about it like this, roughly. A monad on a poset is a closure operator. Interesting. I didn't know that. That's interesting. Had a question about research. How do you get ideas, like the creative process? I know it's hard to answer, but like, what do you do when you're stuck? What do you do when you're stuck? Walk the dog. Yeah. If I had a dog, I would go for a walk. So, if I'm stuck, I maybe go walk myself. But I think it's good to have, yeah, I don't know, sometimes when you're stuck, there's lots of things to do. I mean, talk to people, reach out to people in your network of mathematics, ask questions on Stack Exchange, read more books and papers. Like recently, I was kind of stuck for a long time on my main thesis project, and then I sort of made a bit of a breakthrough. But then it was like, oh, there was this big step that I need to. Well, not a big step, but it was like this annoying theorem that I needed to prove that seems like there's a lot of technical details. And then I was kind of dragging my feet about actually doing it. And then somehow in the first, like, I would have thought I would have come across this paper that was really relevant to my work sometime in the 3.5 years I've been working on this. But for whatever reason, I hadn't. I guess, I don't know. Paper is just not bumped in Google's algorithm or something. And then I found this paper while I was looking for something different. Of course, related to my thesis project. But so I stumbled across this paper, and now that makes that step easy. And now I'm writing it up, and I'm like, wow, it almost feels like I'm not proving anything. Because I just sort of found the right results, right? So, I don't know. That's things to do when you're stuck. How to get ideas. I mean, also, I think I talked about this a bit in a previous stream. Something about creativity, labeled it's like creativity in mathematics or something. But go to talks, like talk to your supervisor, talk to your peers, see what people are doing, how people are thinking of different things. Also go to talks in different areas, because you never know when, it'll be like something totally different, but you'll be like, oh, that has like the same vibes as what I'm working on. I wonder if there's some way to, like, pattern match it into my work. uh Yeah. I also I have a lot of ideas for things that mostly lead nowhere. But some of them, actually, one of them might actually become a paper, a little idea I have in graph theory. I don't know. I don't know if it's paper worthy. I'm gonna try and start trying to get this paper in good shape and maybe send it off to like a graph theorist and see what they say. Um, and but so it's good to have little irons in the fire like that, or just like where, there's some like things I've been thinking about. Like, I think in yesterday's stream I was showing the PDFs I had open that day, and one of them was on some stuff on modules and Merida theory, and I just have silly little questions about that I want to answer for myself. And every once in a while, when I'm stuck, I just go and I work on those. Maybe sometimes more than I should. But I go and I work on those for a little bit and make some progress in understanding. And then who knows? Maybe one day I'll understand something well enough to say something new. I don't know. But those are, yeah, some more ideas about it. But yeah, I think I yap about this a bit more in the office hour that says something. The first word is like creativity in mathematics, so I would go check that out. Do I happen to know any model theorists? If so, what are they like? I don't think I know any model theorists, actually. Yeah. I think I think I have the impression that logicists are more eccentric, maybe, but I have no idea if this is a true impression, a valid impression. Yeah, I don't know how big model theory is these days, but I don't know any model theorists. You're interested in algebraic structures in the category of lambdas, combinators. I don't know anything about that, unfortunately. Is there any prior work on that subject? I had some difficulty finding relevant papers. I have no idea. Can't help you there, unfortunately. Oh, just a Cartesian closed category? Yeah, I have no idea. Well, there you go. There's another term for you to look up in relation to that. Yeah. Okay. Let's see. What else is there to yap about today? Did I have an unfinished thought from up here? No, I think I talked about all the tensor product things. We could always turn to our handy Reddit for a source of inspiration. PTSD about wedge products. Yeah. Actually, someone asked me. Someone asked me to commented that I should do a live stream about differential forms. Maybe. Yeah, maybe I should make a video about them. There's a lot of things I should make a video about. Actually, I made, based on the request from people yesterday, I actually recorded 2 episodes of What's on My Shelf, my office edition, but then I left my SD card at my office, so I haven't uploaded them. But there should be a new episode of that today. But we're starting to get into the books that I haven't read, that I've just collected, so there's not as much to say. in the remaining episodes. I was never thinking about making academia my profession, but wedge products? I took real analysis too, to be whatever felt good until we hit wedge products. I don't think the rest of the class understood anything either. Am I overthinking a relatively simple subject? Do I not possess a mathematically nimble mind? What's a way to understand them so I can finally move on? Good question. Okay, it seems like there's already quite a lengthy, probably good answer there. Oh, there's a few good answers. Here's something that's crazy to me, though. Okay, there's nothing too crazy going on in this post. Looks like there's a few people with good, long answers, and they all posted around the same time, 8 hours, 9 hours. But there is something that crazy that happens on Reddit or all sorts of mathematical forums online where, like, a handful of people will give an initial answer to the question that's like quite, long like this and in depth and like a really good answer. And then you'll see like a post like 5 hours later and someone gives this like half-assed shitty answer. And it's like, why? Why would you bother? Did you not like see the other posts there? Did you think you were contributing in some new way? Like it's perfectly fine to maybe give an answer like 5 hours later, a day later, if, let's say, you think you're offering a perspective that was missed, and you're offering an alternative explanation maybe for the person you think that there's like you could do a better job at explaining it. I think that's fine, that's reasonable, but it's like far too often I'll see a post on Reddit and then like a day later someone just gives like an objectively worse explanation, and it's like, why did you spend the time? I don't know. And I do try to catch myself from doing it. Like, I'll go on a post like this and I'm like, okay, look, there's already a bunch of long answers. I got nothing else to contribute to this. I'm not going to give a better answer than whatever this guy said. Look, they give all of these explanations. Anyways, I'm just ranting about nonsense now. When, in my opinion, would it be productive to start learning the proofs of local Langlands? I'm slowly getting acquainted with automorphic representations and stuff, but I work better when goal-oriented. Yeah, I mean, I think everyone works better when goal-oriented. When would it be start to learning the proofs? Like the proof that the local Langlands is, I don't know. I don't even think I know the proof, to be honest. Like, actually, a lot of my the starting point for a lot of my research is just taking local Langlands for granted. I just say, suppose local Langlands, then blah 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 blah. Like the I mean, technically, to even formulate the Kasdan-Lustig hypothesis, which is the focus of my research, like you need to assume local Langlands, which, okay, I guess is proven in a lot of cases now, but I've never like understood the proof fully. Probably I should. Probably it'd be good to. Like, I think this is the proof of I could be wrong, but I think this is the paper that made Schulze famous initially. Proof of local Langlands correspondence for GLN. Because I think, like, previously this was done by... previously, I think this came out of not Bushnell-Kutsko, but Bushnell-Enyart. Bushnell-Enyart. And I think it was like a whole big book that they needed to write to do this, which probably references and makes use of Bushnell-Kutsko, or at least, those came out in tandem or something. But then I think one of the big if my understanding is correct, please like fact check me on this. But if my understanding is correct, this paper of Peter Schulze was sort of a big deal because, as you can see, it's only 37 pages long, which is significantly shorter than the proof of Bushnell-Enyart. And so he you know, I think that this was the sort of beginning of the introduction of like a new way of thinking about things in the Langlands program, that offered a new proof method, and which eventually evolved into the sort of Langlands type stuff that people are doing today. But I don't actually know for sure. I've gone and I've looked at this paper before and I've skimmed through it, but I certainly can't say I've understood everything. But actually, you know, probably the best thing to do is to go and start learning it now. Start learning it as soon as possible. Yeah, but goal oriented. So I don't know what the goal. Yeah, depends what you consider a valid goal, right? Like you could say, oh, my goal is to understand this paper, but that's not the same, right? That's not the same as like when you're hungry for a particular theorem, you know, and it's keeping you up at night because you're trying to understand something. That's not the same. So I don't know what the goal to set for that is, but yeah, I would. It'd probably be good for me, for my development as a mathematician, to go back and understand this paper in more detail, because it is pretty important to the modern development of the field. There's also what is it? There's another paper I was looking at that geometrization. Is this the one from 21? I think so. It seems so recent. But yeah, but I guess this is a compendium of a lot of results that happened since the 2010 paper. So this is a really crazy. I mean, you know, we're already getting into like geometry of Bungee and all this crazy stuff. But I think this is a good paper to see, because there's all of this stuff you could learn about, right? Like rigid analytic spaces and the stack of G bundles and it's like, gosh, where do I start? And like, why should I care? And like, where do these things come from? And okay, they do talk about some crazy technology in the introduction, but I think this introduction, from what I've skimmed over so far, seems fairly readable, and it's maybe worth looking over, because then you can sort of see, oh yeah, like it gives you an idea of how some of these objects fit together, like perfectoid rings and Farg's Fontaine curve and stuff like this. But again, I mean, I'm speaking as someone who doesn't understand this side of the picture very well, so take what I'm saying with a grain of salt. You're at the point where you get the statements in the paper. At least that. The problem is you can always get into more and more details. Yeah. I mean, yeah, to be honest, like, sometimes I feel guilty as to how little of a lot of proofs in the literature I don't fully understand. You know, like, I feel like when you're younger, when you're learning out of a textbook, you really want to understand every proof line by line in detail, because, for example, you might get asked that proof on a midterm or something, and you want to make sure you knock it out of the park. You also want to understand the material, right, and learn the tools of the trade. And well, that's not different. That's not any different when it comes to papers like this, right? You want to understand how things are proved so that you can use those tools and go prove other things. But yeah, there's also this problem of there's only so many hours in a day, and yeah, there's plenty of proofs. I mean, for the amount of citations I have, for example, certain theorems that I point to, like in my work, like I don't the theorems that I reference, I certainly don't understand the proofs of all of them, not by a long shot, just because there's so much. There's just some technology I have to black box, basically. Um, yeah, I don't know. But you're coming from a more geometric perspective, so Bungie is less scary to you. Then great, great. Yeah, then probably like I love what I do, and I think me and my group do good, interesting work. But I also think it's like the less fashionable perspective on Langlands. Like this is the cool, flashy stuff that all the cool kids are doing these days. So probably like if you have a view towards having like a good career in mathematics, this is probably the stuff you want to be doing, is this Schulze style geometric Langland stuff. So probably getting started on it earlier, sooner than later, is advantageous. I don't know what you need to do to motivate yourself to like, what's the correct motivation to take, but yeah, definitely something like the introduction to this paper might I don't know, inspire you to make forward progress on that. Started watching my playlist on sheaves the other day. I assume the primary motivation of developing the idea of sheaves is generalizing the notion of continuity on topological spaces. Yeah, I mean, I think actually, so sheaves actually, well, they came from a lot of places, but absolute goat legend Jean Leray basically invented sheaves in a prisoner of war camp because he wanted to do math, but he was a differential equations guy, and he didn't want I think the Germans to know that he could do like, differential equations can definitely be applied to like war mathematics. And so he was like, oh, I'm going to work on like really abstract math while I'm in this prisoner of war camp. And then he just like invents sheaves. But in the back of his mind, he had applications to differential equations in mind, right? And so the idea is that like, it's about these sort of local to global principles, right? So like oftentimes you can solve differential equations locally. That's sort of not hard to do, but solving them globally is is much more difficult. And so then the question arises, well, okay, if I can solve it locally in sort of every patch of some geometric thing, how could I guarantee that I might be able to glue together those? How can I glue together those local solutions? And so really, I think this is the idea that sheaves really served to capture, was this idea of going between local and global things. So if you have a global solution, it always gives you like local ones, but how do you glue together a bunch of local solutions, right? So that's the whole idea of like, yeah, if you have some open cover of your topological space, then and you have continuous functions, say into the real numbers or something, defined on each of these, which agree on the overlaps, then you can always glue that together into a continuous function on everything, right? And so it's generalizing that idea of gluing these things together. And of course, sheaves have gone on to like, I mean, this local global idea comes up everywhere, and like solutions to polynomial equations and and then of course sheaves took on a sort of a life of their own once we realized sheaves are actually they're just special contravariant functors, and then there's this whole world of sheaves and logic and stuff, and it's really taken off from that. But yeah, understanding what you need to understand is tough. Absolutely. Yeah. Oh yes, he did also invent spectral sequences in there. Prison can really push a man to such dark places. Yeah. Yeah, absolutely. There's actually, I found a very interesting article once that interpolates sort of his work, because too many terms that start with an S. Yeah. Maybe not enough. I'm an S maximalist. But, definitely sheaves have something to do with analytic continuation. 100%. 100%. Yeah. But yeah, there's this, I don't remember what it's even called, but so it is interesting, right? Because we talk about we talk about things in the modern day era, like, oh, so-and-so invented this, so-and-so invented that. But we talk about where can you learn about sheaves in so in that context of analytic continuation. So probably if you looked at find some book on Riemann surfaces. Probably if you find some book on Riemann surfaces. But even just in the complex numbers, what's a good book? Like, I'm trying to think. There's books I know that deal with complex differential geometry and sheaves of functions, but I don't know one that really hones in on the study of that, just in terms of functions on the complex numbers to start, say. Yeah, I don't know. Maybe check out Riemann surfaces by Farkas and Craw. Maybe that's a place to look. There's Wells' Wells' book on differential geometry. Have not taken a complex analysis course yet. So yeah, probably you want to start there. But sorry, let me just go back to this article, or what I was going to say about history is okay, we talk about the ancient Babylonians, they knew the Pythagorean theorem or something, right? But they didn't have equations like this. This notation didn't exist, right? So them knowing the Pythagorean theorem, they had a poem that was upon taking the triangle of a length of the given side, then the combination of the blah blah blah. That was the Pythagorean theorem, right? Or in the same way, there's just so many stuff where it's this person knew this in the 1400s, but if you go back and read their actual original work, it does not obviously look like anything that we write today, right? So we've really changed the way that we write things, and so those statements are still true in a moral sense, but the way that people did math even a couple hundred years ago, it looks very, very different from the way it's done today. So we call things so and so's theorem and whatnot, but sometimes it looks very, very different. And so in this article, they talk about Jean Laray's original papers on things like spectral sequences, but I mean, if you were to go and look at those papers today, you would look at that and you wouldn't immediately recognize that he's talking about spectral sequences, right? Because that language didn't exist. We've and I think I talked about this recently too, just on the way that we improve how pedagogy changes and our understanding of math changes, and we come up with better and better ways to explain things, right? So things that are on the cutting edge today that are difficult to understand because we're still grasping at them, this could become undergrad material in 50, 100 years, whatever. And so anyways, if you like math history, there's some decent article about connecting Jean Laray's original perspective to spectral sequences in the modern era. Yeah. One of the most important things to realize is that in 50 years we'll be calling these things something else. Yeah. Probably. I mean, some names remain stable, but yeah. Yeah, exactly. Anyways, I'm gonna call it for today. The coffee's almost done, so the proofreading urge is hitting hard, and effective mathematical pedagogy in elementary school. Yes, there's a lot to talk about there. I don't stream on Thursdays because I got to be up extra early. But so have a good 2 days of writing proofs. May or may not see y'all on Friday. But yeah, prove hard today.